All right, so let's go ahead and get started. Again, hi, welcome to AP Calculus. My name is Leah. I tutor mostly SAT and ACT with Prep Matters, although I do a lot of different high school math courses as well. And then I am a full-time high school math teacher. I teach AP and IB courses in high school. And I see some names here that I recognize. Hi, and I miss working with you, and I am excited that you are here. And some that I don't, so welcome. And I hope that you enjoy working through some calculus today and through the next couple of weeks. So we're going to do this AP Calculus session every Wednesday from now through the rest of April, going through the different parts of the AB curriculum on Wednesdays, and then 2 extra sessions on the last 2 Fridays in April to go through parts of the BC curriculum. So I am assuming that some of you are in a full year AB course, and some of you are in a full year BC course after taking AB last year. And then there are also some of you that are going through an entire year of AB and BC together. So that puts us all at very different levels and speeds of calculus and all of that. So we're going to go through some of the basics that just kind of connect everything. And then some of the specifics for just the BC curriculum on those last 2 Fridays. So as we all know, the AP test is going to be a little bit different this year. One of the things that is going to be the most different is the actual type of questioning, which hopefully your teachers are communicating with you as we go through the school year. AP is going to publish most of that information on Wednesday or on Friday of this week. I do see questions coming through, and I'm going to get to some of them as we're going and some of them at the end. So please keep asking those questions as we go through. I'll answer them as we talk. But we're going to get all of this information about the AP exam on Friday of this week. So this session is going to look a little bit different than what our future sessions will look like for 2 reasons. 1, because we don't have any of that information yet anyway. And 2, just because the content of what we're going to talk about today is very different than the content that we're going to talk about for the rest of the sessions. This is still the building blocks of calculus today. This is the basic stuff. It's not really even enough to build an entire free response question. So keep all of that in mind as we go through things, as we go through the different things of material. And then to answer the question that did just come through, yes, we will keep holding these classes. So just one logistical thing, I am going to be writing a lot through this. It's really hard to talk about math without actually writing. So I'm going to take the screen off of me so that I can write on this screen and the camera view doesn't just, sit at the ceiling. So you're not going to see me through most of this. I will come back on at the end and actually summarize things and talk through things, but I am going to have the camera view off for most of it. I'll still check in with your questions here and there. If I don't answer your question as we are going, please keep sending them. I will look through all of them again at the end. There will also be an email address at the bottom of all of the slides that I'm going to work off of that have an email address that you can use to answer or to ask any questions that I don't necessarily answer as we're going through this. So let's go ahead and get started with what we're going to talk about today. And again, I just kind of mentioned this, but today's session is going to look a little bit different than most of the other sessions that we will be going through, because this is the background information of calculus. These are the building blocks of calculus. So from a calculus perspective, this Unit 1 and Unit 2 material, it's not a lot. It's not something that we can really make an in-depth free response question about, but it is something that kind of permeates through everything that we do. This is essentially the alphabet of calculus. So we really need to focus on learning the letters and learning the rules of the letters and which letters work together and all of that information before we can really form words or sentences or even paragraphs. And then really, until we're really comfortable with these particular letters, these particular pieces, we can't actually talk about the really in-depth pieces of calculus. So the remaining sessions will look a little bit different than the one that we're doing right now, because again, we're going to focus a lot more on those background skills today. I'm also going to urge you to kind of do something that I'm going to guess most of your math teachers would never ask you to do. And I'm gonna urge you to really just sit back and actually watch this like it's actual TV. Again, this is the foundation of calculus, and these are the concepts and ideas that you want to be able to quickly explain and not just necessarily do. So as we go through this, I want you to kind of keep that in mind. Think about how you would explain this to somebody else and not necessarily just read a problem, do something. Especially as we go into an unprecedented testing situation, it's going to be a lot easier to get through questions really quickly if you know what you're doing, if you know why you're doing what you're doing, and not just, I memorized my way through this type of problem, this type of problem, and this type of problem. So again, I urge you, again, I know this is math, I know we're used to writing, I know that we're mostly comfortable with having a pencil in our hand, seeing a problem, and just instinctively jumping into it. I urge you to not do that. And I'm gonna urge you to just truly sit back and just watch this. This is being recorded, so you can go back and actually pause it and work problems later, but try to just kind of think through this with me today. For those of you that did get through most of your content this year and that started reviewing in class, hopefully today is a really quick kind of review of what's already in your brain really well. And you can kind of try to almost do this for me, almost think about what I'm going to say, what I would need to say about something, and do it and talk through it. For those of you that did not start reviewing yet, this is going to be kind of a flashback to the month of September in your actual calculus class. And for those of you that are somewhere in the middle of some form of calculus, again, this is the beginning of the year. This is the beginning of the year, whether you just reviewed this the week before school closed or you haven't actually thought about this since September, sit back and try to think about the theories that we're talking about and all of the actual stuff that we're working on. So here's our agenda for today. I'm going to mostly focus on actually interpreting the derivative of a function. This is the big key concept of calculus and kind of stems through everything and leads us to what we're talking about. The rest is going to come in and out of the things that I talk about, and it's going to come in and out of the different pieces. But this is our big focus, interpreting that actual derivative of a function. Now, before we do this, I want to let you warm up your brain for a minute and go ahead and look at this. Look at all of these limits. Sorry, I'll stop clicking all over my screen. Look at all of these limits, and I want you to quickly see how many you feel like you know how to actually evaluate right away. I don't want you to do them. Try not to take out a piece of paper and a pencil and write them down and scribble stuff out. Look at them and see if you know how to do them. Look at them and see if you could tell somebody what to do. And I'll just pause for a couple seconds and let you try to do that. All right, hopefully that was not a miserable task. And you can kind of just think about how you would do these. I'm gonna do the same thing with another set of problems here. Here there are 6 functions, and I want you to look at them and think about whether or not you know how to find the derivative of these functions. Don't necessarily do it. Again, think about how you would do it. Would you use a product rule? Would you use a chain rule? Would you use a combination of rules? Do you know the particular derivatives that you need, whether you need to know a trig derivative or a derivative of an exponential function, something like that? Think about how you would do these. And again, I'll give you a couple seconds here. Okay, so some of you are maybe very miserable when given a task like that. You just want to throw that pencil on your paper and actually do the math, actually find a derivative, actually do something. Others maybe love this way more than actually doing math. We will actually do all of these at the end. We'll look through these. These are some of those basic building block skills, just quick derivatives, quick limits, things like that, that we'll talk about as we go through today. But again, I want to emphasize thinking about what you're doing, why you're going to do what you're going to do. Do you need to use a product rule? Do you need to use a chain rule? Are you going to substitute in a number? What is actually happening? Could you explain how to do this problem to somebody else? Not necessarily just, let me throw my pencil on a piece of paper and do this, but could I explain this to somebody else? And again, we will come back to those. That was just a quick warm up, whether you got through all 6 on each slide really quickly, 5-second process for each, or whether you spent most of your time thinking about one. Doesn't matter where you are right now. Just use this as a good gauge for your thought process for today. All right, now we're going to talk about what in the world calculus actually is. Before we go into evaluating those limits and finding those derivatives, I want to go all the way back to Algebra 1, and I want to think about a linear function. Nice, easy, pretty linear function. You could show this to somebody in 8th grade and they would say, oh great, y equals mx plus b. There's a linear function. And that's exactly what I want to focus on right now. Also, just as a logistical thing, I'm going to zoom in and out here and there to write in a mostly legible fashion. I promise I will always zoom back out so you can see everything before I move on to the next part. So linear function, y equals mx plus b. We know this. We've known this for years. This is probably the least scary type of function out there. This is exactly where we want to start when we start trying to think about what calculus actually is. And the reason that we want to start with this is exactly for this y equals mx plus b situation. Y equals mx plus b, y equals m, the slope, x plus b, is important because it shows us so clearly that a linear function actually has a slope. We have that m, we have that constant rate of change. If I say, for instance, that this function is y equals 1/2 x plus 3, then I know that for every increase of 1 in my x values, my y value increases by 1/2. And that's a really great thing to know. It doesn't seem that important in actual Algebra 1 when we learn this, but by the time we get through all of the different function families in Algebra 2 or pre-calc, we should start to realize that this is a situation that's really unique to linear functions. This ability to know how the function is changing at any single x value over its entire domain is completely unique to linear functions. For this particular linear function, I know that when x increases from 700 to 701, y increases by 1/2. And when x increases from -40 to -39, y increases by 1/2. And when x increases from anything to the next x value by 1, that y value increases by 1/2. And that's so important to note here because we kind of take that for granted in algebra, but it's only true for linear functions. If we look at another type of function, so if we look at some of these nice, fun, beautiful pre-calc functions, an exponential function or a rational function or a polynomial function or a radical function or really any type of function, a trig function, a logarithmic function, anything that's not linear, we don't have that ability to talk about a constant rate of change. There is not a slope for these functions. I can't just say for any one of these functions that as x increases from 700 to 701, great, this is how y changes. Or as x increases even from 0 to 1, great, here's how y changes. I don't know, I don't have that ability. We do, however, have the ability, I'm just gonna zoom into this polynomial here. We do have the ability to talk about this between two different x values. We can always say, for instance, that between this x value and this x value, my rate of change, this function is changing by a positive value. And between this x value and this x value, for instance, that rate of change is negative. Between this x value and this x value, my rate of change is positive, and it's way more positive than it was here. In other words, the rate of change, what we just talked about as slope in the linear world, that rate of change of this function is changing. And this is the entire point of calculus. The entire point of calculus is talking about how functions change. Just like geometry is the study of shapes and trigonometry is the study of angles, calculus is the study of change. Specifically, Calculus allows us to find some type of function that describes the rate of change of another function. And hopefully, for those of you that are really already into your review or really connecting pieces, you already know what that function is called. Calculus lets us find a function that represents the rate of change of another function. That is our derivative. So look, I already almost moved on without zooming out for you. Let's talk about what I just said really quickly in actual mathy words. So with points and functions and all of this really fun stuff before we dive into some actual problems. Let's say that we have this function, some type of weird looking polynomial-ish function. And we have 2 points on this function. I'm gonna zoom in a little bit here. So let's give ourselves a point Q and a point P. And I'm going to say here that Q has the x value of x, so then therefore has the function value of f of x, and P has the x value of x plus h, where this distance between my two x values is h. So then P has an f of x value, or a y value of f of x plus h. And hopefully you already know exactly where I am going and can finish this conversation for me. This should look very much like your limit definition of a derivative. And that's where we're going here. That's what we're building. But I do want to just stop and pause and do this a little bit slower than you have probably been doing for the last couple of months to make sure that this idea is really strong in your brain, so that then once we do get into those complicated free response questions, we always have this to fall back on. So now if we're looking at this and we want to figure out the rate of change between point P and point Q, or more accurately, between point Q and point P, based on what we know before we learn calculus, we really have no way to do this. We would have to go back into the world of algebra and make some kind of linear function between Q and P and find the slope of that line. The line segment that I just drew has an equation. I can write y equals mx plus b, some m, some b, y equals mx plus b for this line segment right here. And this line segment that I just drew, this line segment between Q and P, that's a line that's secant to the actual function. A secant line touches a function twice, or intersects a function twice. If we want to actually do this, we're going to go all the way back to our Algebra 1 formulas. And you may have noticed as you went through calculus, the calculus becomes the easy part of calculus. The algebra becomes the hard part of calculus. As we actually go back to Algebra 1 and look at our formulas for slope, we can figure out that the slope between this line, the slope of this secant line between point P and point Q would be represented by f of x plus h minus f of x over x plus h minus x. And then right away, we can clean up that denominator so well. And we know that the slope of this secant line is f of x plus h minus f of x over h. Again, hopefully, if you're sitting through calculus for lots of months, you know exactly where this is going. That is the goal. That is ideal. Here's your slope of your secant line. What happens here is that we can start manipulating this in order to move this point P closer and closer and closer and closer to the point Q. As we move this point P closer and closer and closer and closer to this point Q, we make this value of h as small as possible. We're starting to make secant lines that are going to much more accurately represent how the function is actually changing around Q in this area. If we keep decreasing this value of h, we keep sliding this point P closer and closer and closer and closer to Q, again, making this line segment between Q and P smaller and smaller and smaller and smaller and smaller, we're going to get a much more accurate representation of how this function is actually changing, what the rate of change of this function is at Q. What we will ultimately end up with, let's see what color I didn't use yet. What we will ultimately end up with is, instead of a secant line between Q and P, we will end up with a tangent line at Q. Remember that secant means intersecting twice, tangent means intersecting once. Now we can't actually make H 0. That's going to mean that Q and P are the exact same point. We can't find a secant line between 2 points when the points are the same. But we can make H as close to 0 as possible. And throwing a little bit of calculus into our information right here, we would see that that would give us this formula right here. If I want to keep moving this point P closer and closer and closer and closer to Q, decreasing that value of H, making H as close to 0 as possible, that would be represented by this. The limit as H approaches 0 of f of x plus H minus f of x over H. And now hopefully we just have all the light bulbs going off if they haven't yet. Here's your limit definition of a derivative. And this is exactly what I want you to keep in mind truly as you go through every single piece of calculus. Every single piece of calculus that you go through, we want to go back and think about the ultimate goal of what we just looked at here, the ultimate idea that calculus is the study of how a function is changing. And think about this idea that that instantaneous rate of change, the rate of change at one particular x value, is the slope of the tangent line at that x value. The average rate of change between 2 points, average rate of change, the average rate of change between 2 points is the slope of a secant line. The instantaneous rate of change is the slope of the tangent line. And that's what we know of as the derivative. Instantaneous rate of change, tangent line, derivative. Average rate of change, secant line. Again, very basic from the idea of a calculus class. This is day 1, maybe week 1. But something that you have to keep in mind to really understand what free response questions are asking you. Connecting those ideas that we just talked about right here. So I'm going to take this into a question. I'm going to pause this here for a second just to kind of explain to you what's going on and then check into some of your questions. And again, I realize, you realize these are not full AP questions yet. We did not just cover enough information in what I just talked about to form an entire AP free response question, but these are parts of AP questions. And I want you to just keep that in mind as we go through this. So also notice that there are a lot of blanks in this question, and I did that on purpose. I want you to not be able to just plug stuff in right away or do anything. I want you to think about what's actually going on here and think about what's actually happening. And I'm going to change this question 3 different times for 3 different starting points. But let's say that we are given this function, f of x equals cosine of 2x, and then 3 different pieces of information or 3 different question stems. We want to find the average rate of change between 2 points, an instantaneous rate of change at a specific point, and then also write the equation of a tangent line. And I'm going to start talking through this in a minute, but go ahead and just think about how you would do that. Think about how you would find all of those things. Okay, so thinking through what you're actually doing here, just like we just talked about, average rate of change, that has to be between 2 points. Let me unhighlight everything first, sorry. Average rate of change, that has to be between 2 points, whatever 2 points I might throw in there. Instantaneous rate of change at a specific point, that has to be at a point, 1 point. And then the equation of a tangent line. And I threw this last question in here because this, and I tell my class this every single year, and they roll their eyes at me every single year, and then they prove me right every single year. This is one of the most missed pieces of an AP exam, always. This part right here. This basic Algebra 1 question, every year. And I think that happens because you spend months doing hard calculus problems and then forget how to do basic algebra and forget how that calculus actually connects back to algebra, which is again why I just wanted to go through the beginning of what we just went through. I want you to be able to make those connections between calculus and algebra, make those connections between everything you've ever learned and the actual calculus processes that you have learned all year. All right, so let me throw some points in here and let you try to think through some problems. Again, I don't necessarily want you to scribble things down. Just think about them. Try to figure out what would actually happen. So I'm gonna go just into average rate of change first. So find the average rate of change between, let's do x equals 0 and x equals pi over 2. And again, our function was actually f of x equals cosine of 2x. So again, hopefully you can do that pretty quickly, but again, I want you to think through what's actually happening there. If you think about a graph of this, we have some form of trig function. It's a pretty not great trig function, but let's pretend. Actually, I'll fix it. So the period of this function is pi. Hopefully we remember how to figure out all of that from either Algebra 2 or pre-calculus whenever you learned that. This is your value of b. Period of a cosine or sine curve is 2 pi over b. So 2 pi over 2 in this case. That makes this pi over 2. 3 pi over 4. And pi over 4. I'm sorry for going weirdly out of order on this. And if we're thinking about an average rate of change, all that I really want to know is what is the slope of the secant line between these 2 points. Find the y values, find the x values, plug them in, great, there you go. Average rate of change, slope of the secant line. If you are going through and actually doing this problem, it's -4 over pi. If we're thinking about the instantaneous rate of change, we don't necessarily want that average rate of change between 2 points. We want the instantaneous rate of change at 1 point. I want to know the slope of the tangent line. Let's do this at x equals pi over 6, and I'll actually do this one. So instantaneous rate of change at x equals 6. So instantaneous rate of change, that slope of the secant line. If I go back to this graph, and I wanted pi over 6, that's somewhere over here. That slope of the tangent line would look something like that. That we can't just estimate off of a graph. So that one we'd have to actually work for. And in this case, we can find the derivative. So f of x equals cosine of 2x, that was our function. The derivative, f prime of x, would be 2 sine of 2x, actually be -2 sine of 2x. And that requires both knowledge of a trig derivative and knowledge of the chain rule. I'm not going to emphasize that a ton in this section. Again, this session is way more theoretical than they will be overall, but I'm also assuming that as we went through the school year, we got really good at the actual doing the calculus thing and started to lose the what does the calculus mean thing. So we're focusing on that a lot more today. So there's our derivative. If I want to evaluate this derivative at pi over 6, that would mean that I'm actually looking for -2 times sine of pi over 3. And sine of pi over 3, look at how this is a nice reminder that you need to know that unit circle really, really well. Sine of pi over 3 is root 3 over 2. So -2 times root 3 over 2. And that's going to give us a value of -root 3. That instantaneous rate of change at x equals pi over 6 is -root 3. If we go back to our graph, does that make sense with what we said? Yeah, we knew that there needed to be a negative slope. The tangent line at x equals pi over 6 has a negative slope. Our derivative must be negative. The derivative is the slope of the tangent line. If we were really great with fractions and irrationals and radicals and all of that, we could also compare the slope of that tangent line to the slope of this secant line if we had actual values for a and b. I'm going to hold off on that because I want to really make sure that you know how to do this last part here, right? The equation of the line tangent to the function at, let's pick another one so we can really practice our trig values. And let's do this at x equals 2 pi over 3. So again, our function was f of x equals cosine of 2x. We want the equation of the line tangent to the function at x equals 2 pi over 3. So again, all the way back to Algebra 1, What do we have to know in order to write an equation of a line? Well, we need to know the slope. I need to know the slope of a line. There's no way around that. The slope of the tangent line, again, derivative. So again, I need that derivative. We already have it from the problem before. Negative 2 sine of 2x. This time I want to evaluate, I don't want to do that. I want to evaluate this at 2 pi over 3, which would be negative 2 sine of 4 pi over 3. Think about what that is. Think about your unit circles. Third quadrant, negative sine of 4 pi over 3 is negative root 3 over 2. So we're going to get negative 2 times negative root 3 over 2. We're going to get a positive root 3. So our slope of the tangent line at x equals 2 pi over 3 equals root 3. I would urge you to then go back to your graph, back to thinking about a graph, and think through whether that makes sense or not. So 2 pi over 3 is between pi over 2 and 3 pi over 4. It is, let me get a different color. It is like here-ish. If I drew a tangent line, it would have a positive slope. Great, so there's an easy way to check yourself. Now that we have the slope of a line, we also need a point on that line. There's my point. I already know the x value is 2 pi over 3. I just need to know the y value. I need to know the function value when x equals 2 pi over 3, and that I can get from right here. Cosine of 2 times 2 pi over 3, so cosine of 4 pi over 3. Cosine of 4 pi over 3 is negative 1/2. So I have the slope right here. I also know that I have the point 2 pi over 3, negative 1/2. There's my x value, and there's my f of x value of the original function. That tangent line shares this one point with the original function. And now here's the part that we never remember. Here's the part that is one of the actual truly most missed things on an AP Calculus AB exam, equation of a line. I recommend point slope form just because it is by far the easiest to use. And that's y minus y1 equals m x minus x1. Hopefully you've been using this throughout your year in calculus, but if not, make sure that you jot that down and actually remember that this exists. If you haven't touched this really in 3-4 years of math, make sure you know this point slope form. It's going to make your life the easiest when you get to these types of questions, because again, we already know the slope and we know a point. So right away I have y minus negative 1/2, so y plus 1/2 equals root 3 times x minus 2 pi over 3. And there's your equation of a tangent line. Often in multiple choice questions, just as a small caveat to this, in multiple choice questions, this is usually then taken all the way into slope-intercept form. Since you will not be working on multiple choice questions, you don't have to continue to manipulate this until you match an answer choice. Whatever form you leave your answer in, as long as it is a form of an equation of a line, you're good. There's the equation of a line. And that's the connection between all of these different algebra pieces and calculus pieces. Again, keep these in mind as we're going through things. I'm going to slightly manipulate this question now. I want to do the same exact thing, but just talk about what would happen if instead of being given a function, we were given an actual graph. I'm not even going to necessarily fill in these blanks here. I just want to talk about this briefly, but if we were given this graph instead of an actual equation, instead of the algebraic form of a function, how would we handle a question like this? How would we do a question like this? So think about this for a couple seconds. Okay, now hopefully you really just figured out the fact that this relies heavily on the graphical aspects of everything that we just talked about. Average rate of change is the slope of a secant line. As long as I'm given 2 points, I'm going to find the slope of the secant line between them. Great, that part's nice and simple, and that part doesn't even really rely on where those points are. You can draw a secant line between any 2 points that you want to. Now, you would also obviously have numbers on your graph. This one does not have any, but average rate of change, slope of a secant line. This is the part of the problem that's a struggle here. We want to find the instantaneous rate of change at some particular point. If we are not given the algebraic function, we can't just run into our derivative rules and get a derivative, plug stuff in, go for it. We don't have that option anymore. We have to rely on that graphical idea that the instantaneous rate of change, the derivative, is the slope of a tangent line. This is where this becomes a problem. We can really only do this, we can only really answer this question if we are zooming into an x value where the slope of the tangent line actually follows or where the tangent line would actually follow a linear pattern. I would not be able to, for instance, find the slope of a tangent line here at point B because I can't just guess what that slope is. I could draw it like that. I could also kind of mess it up a little bit and draw it like that. I could draw it like that. I really have no idea. We can, however, figure out the slope of the tangent line right here because it's exactly the same as the slope of the actual line. So long answer there, but important piece here, you can find an instantaneous rate of change from a graph if the part of the graph that you are looking at or working off of is linear. So anywhere, any of these x values right here could go in this box. Anything over here could not. I cannot find the instantaneous rate of change for any of those x values unless I have more information. So then same thing is true over here, writing the equation of a tangent line. I am not on a pencil right here. This last part, write the equation of a line tangent to the function. If it's in that red box part of the x values, great. You can do this exactly like we just did the question before. Find the slope of that tangent line, which is the same as the slope of the actual line, and go from there. If we're working off of an x value over here in this kind of more circled part of the x-axis, this would not be possible. And then one more slight change for this. Instead of being given a function algebraically like the first part, and instead of being given a graph like the second part, we can be given a table. This one is the one that is going to lead a lot into a specific type of AP free response question that once we combine this with integration is one of the more common things that we can see on an AP exam and we'll work through eventually. But let's think about how we would handle this if we were given a table. We're not given the function. We can't necessarily write the function. We can think about what it looks like, but we can't write C of t equals blah, blah, blah. We probably don't want to graph this. We could graph points, but we really couldn't even graph a function. All we have is this table of information. Ideally, you can look at this and see that this looks fairly exponential. I would assume this is an exponential function or some variation of an exponential function. That looks like the best modeling of this. So then we can kind of think about what that average rate of change would look like, that slope of the secant line, and that instantaneous rate of change or that slope of the tangent line. We just can't necessarily turn this into an explicit function or an explicit graph. I can still find that slope of a secant line between whatever two values I wanted to, let's say 1980 and 2000. Great, secant line between this and this. Throw your points into your secant line slope formula, and there you go. Again, this second one becomes the problem. Find the instantaneous rate of change. You can't find an instantaneous rate of change here. You can, however, find an approximation for the instantaneous rate of change. Sorry. And this is a very commonly done free response piece right here. So if I say find the approximate instantaneous rate of change at, let's say for instance, 1990, we could do that. Just like we did in the very, very beginning when we had that point P and that point Q, we can pick a point P and a point Q on either side of 1990, and we can use the slope of the secant line in order to estimate the slope of the tangent line. It won't be good, but it will be the best that we can do. And there's two different approaches to this. The most common one, the one that's shown in most AP free response questions, is to find the slope of the secant line between the point on the left and the point on the right of what you're trying to get to. So in this case, 1985 and 1995. We would use the slope of the secant line between 1985 and 1995 to estimate the slope of the tangent line at 1990. Second option, and this is the one that's usually shown in more college-heavy calculus textbooks, is to find the slope of the secant line between 1985 and 1990, and to find the slope of the secant line between 1990 and 1995, and then to find the average of those two slopes. Either one would be completely fine for this as long as you're showing your work. Again, once we get through this first session and start going through free response questions much more in depth in the remaining sessions, I will talk about a little bit of scoring guidelines and things that we need to make sure is in our writing versus things that don't really matter, all of that type of information. But as long as you're showing your work and your methodology, you would be okay here. And then again, same kind of idea for this third part. If we're writing the equation of a line tangent to the function at some particular point, we're going to need a slope of a tangent line. We can't necessarily get the slope of the tangent line, but we can estimate the slope of a tangent line. And I want to talk about just a couple of quick things before I move on to one more problem stem. One thing that I really recommend that you are doing as you're working through AP problems is pausing at the end of every single problem and thinking through three specific things. Thinking through what calculus knowledge you needed to complete that problem, what algebra knowledge you needed to complete that problem, and what trig knowledge you needed to complete that problem. So for instance, the first one that we did, the one where we started with an actual function, f of x equals cosine of 2x. In order to get through those three question stems that we were given, we needed to have really solid unit circle knowledge. So trig knowledge that we needed to know the unit circle. I needed to know sine of 4 pi over 3. I needed to know cosine of 2 pi over 3. I needed to know my unit circle values. Algebra knowledge that we needed to know the equation of a line. I need to know what point slope form is. I need to remember that formula, and I need to be able to use it. It's a really great idea to start formalizing all of that as you go through problems. Start really thinking through those things and listing it. I always recommend to my students having one list of calculus knowledge information, and one list of trig knowledge information, and one list of algebra knowledge information. So 3 separate sheets of paper. And every single time you go through an actual question, go back at the end, pull out those 3 sheets of paper and write down the things you needed to know. So that by the time you actually get to a test in May, in June, in whenever it is, you have that information in front of you and you have a quick kind of cheat study guide to look through and say, okay, here's all the algebra knowledge that I needed in the last 50 AP problems that I did. I needed to know the equation of a line. I needed to know how to factor using difference of perfect squares. I needed to know how to solve a quadratic using a quadratic formula. And all of that. And all of those kind of algebra skills that just seep out of our brains once we only do calculus for a year are back in the front, and we know that we need to know them. I recommend that you do that all the time. It's time consuming, it's annoying, and I know that you just want to go right into the next problem, but that is one of the most helpful things that you can do as you're studying. So I'm going to go back to a problem now. This is what I just talked about. And now we're going to look at this problem. I already have this one kind of filled in for you because I want to talk about a lot of really seemingly disconnected but actually connected pieces here. But I'm just going to pause a couple seconds, try to just read this and see if you know what to do. Okay, hopefully that was enough seconds to think about knowing what to do. Also, the answer, FYI, does not exist, which is the most common answer that I generally get to this question at first. I love this question because so many people do say that this limit does not exist right away for just one small, tiny reason. And this question really emphasizes a lot of great limit information, derivative information, and then some ideas about continuity and differentiability. So this truly is a 10-second question if you really know what you're doing, if you're all the way through reviewing already and are just kind of re-emphasizing pieces, this should be a super quick one. If you're just starting your review process, this one might be a little bit trickier than it really looks. So again, I'm going to drag this one out way more than I would really do on an actual test, because I want to emphasize a lot of pieces. Even if you think you know exactly what you're doing on this one, listen to all of these pieces. Make sure you actually have all of this down. So first thing that I want you to think about, just like we thought about with the last one, what does this function actually look like? If you look at this g of x equals -4 times the absolute value of x plus 2, what would that look like if you graphed it? Hopefully by now, after you've just listened to me talk for however many minutes this has been, you've realized that you really need to know what your function families look like. All those Algebra 2 pre-calc, parent function, transformation ideas, they're still really important. They're really helpful in connecting the theories and the ideas of calculus and algebra and all of that if they're still in your brain. So this is an absolute value function, obviously. It is a absolute value function that is transformed 2 to the left, has a vertical stretch of 4, and it's reflected over the x-axis. So it looks something like this. It actually touches the x-axis. Okay, so we have a function that looks something like this. Now, hopefully, you're looking at this, and the first thing that you're thinking when we're going to talk about a derivative is that this function is not differentiable at its vertex. This function is not differentiable. There is no derivative at its vertex, which unfortunately is the exact x value that we need to use. All of that being said, that's fine, because we are not talking about the entire derivative. We are only talking about the derivative as we approach -2 from the left. So we're really only talking about half of this absolute value function, half of the derivative function, the approaching of -2 from the left side. And that is that little tiny thing right there, that little tiny minus sign, that is what changes this question to not have an answer of does not exist. So I'm gonna, again, drag this out way more than we need to take it. I'm gonna take this into two different ways, right? Or two different methodologies right here. If we think about this graphically, we know that we need to figure out the limit. I'm gonna erase all of this for you so I'm not scribbling everywhere. We need to figure out the limit of the derivative, which means we need to know the derivative. Derivative, slope of a tangent line. Slope of a tangent line from the left side of -2, well, that means I really don't even need this. All that I want to know is the slope of my tangent line, and let's just pretend that this actually connects. I need to know the slope of my tangent line right here. Well, if I draw a tangent line, it looks like this. The slope of that tangent line is exactly the same as the slope of the left side of this absolute value function. We can figure that out, pick 2 points on it, throw it into a slope formula, great. Your slope is 4. That means the slope of the tangent line is 4. That means that the derivative is 4. All of that being said then, if I want the limit as x approaches -2 from the left of my derivative of g of x, well, the derivative is a constant value. The derivative is 4. That means I'm finding the limit as x approaches -2 of 4, the limit of a constant value. The limit as x approaches -2 from the left of 4 is 4. That's the first way to do this, just graphically. Think about what this looks like. Think about what this means graphically. Go for it. Go through all of your algebra. Second option, which would be a much more important option if this was a complicated function to graph, is to go through this entire thing algebraically. And I want to emphasize this because for most absolute value questions, we are going to have to work through them algebraically. And the easiest way to algebraically work through an absolute value function is to make it not an absolute value function. What I mean by that is rewrite it as a piecewise function. So if I rewrite this as a piecewise function and say that instead of saying g of x is the absolute value function, instead of that, say that g of x equals -4 times x plus 2 if x is, let's see, greater than -2. If x is greater than -2, the absolute value of x plus 2 is exactly the same as x plus 2. If, on the other hand, x is less than -2, then the absolute value of that expression, x plus 2, would be its opposite, would be the negative version of that, which would mean that I have a function that looks like this. No matter what calculus you're really doing with an absolute value function, it usually is the easiest, with the exception maybe of this easily graphable one. It really is the easiest to write it as an as a piecewise function, to think through what happens to the right of the vertex, what happens to the left of the vertex, and how do we actually need to write this as two different functions. Once we do that, then we can figure out, okay, well, the derivative in this particular case, what am I writing? Sorry. The derivative in each particular case would be 4 or -4. Nice, simple derivative right there. And then we're right back in the same position that we were in for the graphical perspective. And one thing that I want to call your attention to and just think about right here, I said that x is less than -2 and x is greater than -2. When x equals -2, either one of these pieces works. I could put that equal to sign on either one of these. I could throw it here or I could throw it here. Not both, but I could throw it in one or the other. For the derivative, that is not true. Because remember what we just talked about in the beginning, the derivative does not exist at x equals -2. So in this case, I cannot throw in an equal sign on either one of these. The derivative does not exist at -2. So again, both ways will take us to this actual answer to this question of 4. But what I really want you to see here and really want you to think about here is that that derivative does not have to exist at x equals 2. This function does not have to be differentiable at x equals -2 in order to evaluate this limit, because we are evaluating the limit from the left. We are not asking what the value of the derivative is when x equals -2. We're asking what the value of the derivative is when x is really, really, really close to -2 on the left side of -2. So on the -3 side of -2, not when x actually equals -2. Now, just another review from this question. I love this question because it does lead into really good conversations in a classroom about differentiability and continuity. Couple of quick things from this. Every function is not differentiable at every single x value. We cannot find a derivative at every single x value. This is a really good example, this absolute value function, where we cannot find a derivative at its vertex. And if you think back to, again, what I have been emphasizing lots of times, what I have said probably 100 times in the last 40 minutes, the derivative is a slope of a tangent line. If we have a point of a graph where we cannot draw a tangent line, we cannot find a slope of said tangent line, and then therefore there is not a derivative. That is essentially what you need to remember about differentiability. If we look at a function, this is going to be a brand new function here, something that is not really related to the problem. I'm just going to use the same screen. Let's say we have a function that looks like this. I cannot draw a tangent line right here. I wouldn't know if I'm coming from this way, if I'm coming from this way. I cannot draw a tangent line. That function, this function right here, is not, let's call this 5, is not differentiable at 5. It's not differentiable at 5 because it is not continuous at 5. Think about continuity of a function as just, can you trace that function left to right without picking up your pencil? No. If I actually trace this here, I have to physically pick up my pencil in order to continue from 5. This is jump discontinuity here. The function jumps to a new value. It's not continuous at 5. A function is not differentiable at every x value that it is not continuous. A function needs to be continuous first to be differentiable. This function is also not differentiable here at 7 because I cannot draw a tangent line. Am I drawing a tangent line this way? Am I drawing a tangent line this way? I don't know. I cannot draw a tangent line. In most calculus classes, you probably called that a cusp or a corner. It's just really anytime that there's a sharp turn or a sharp curve in a graph, we can't draw a tangent line. That means the function is not differentiable at that point. So points of discontinuity, points of sharp turns, whether you called them cusps, corners, sharp turns, whatever, points of sharp turns, and then one more, points of vertical tangency. So let's say here at 3, my tangent line is a completely perfect vertical line. The slope of a vertical line is undefined. That means that the derivative is undefined. Derivative, slope of a tangent line, undefined. Therefore, there is no derivative. The function is not differentiable at points of vertical tangency, points of discontinuity, and points of sharp turns, cusps, or corners. So just a little bit of background theory. Now, slight manipulation on this problem. Look at everything that we just needed to really know in order to get through the problem with the stem that I already wrote in there. If I change the stem a little bit and say, okay, well now g of x is a rational function instead of an absolute value function. And instead of finding a limit at a nice, beautiful integer value, I'm going to try to find a limit at infinity. This is a completely different problem now, although it looks very similar. This time I have to think about what my rational function might look like and think about how I evaluate limits at infinity. I still need to be able to work through the same type of information, think through differentiability, continuity, all of my different rules, think about what this is actually asking, but mathematically, all of the math that I'm going to do now is very different than the math that I just did in the problem before, even though this structure of the question looks almost exactly the same. If I change this function and I change this limit, very different math. And that is why, again, I want to keep emphasizing thinking about what you're doing, not just looking at something and trying to instinctively jump into doing math, because one little tiny change in a problem can completely change the way that you do the math. In this case, it's probably, hopefully, not as challenging to find the derivative. This is a quotient, apply a quotient rule, great, there's your derivative. Then we're going to try to figure out what that limit as x approaches infinity is of that particular derivative. So again, different math, very similar question. And I'm going to go through limits at infinity in a minute, so I'm going to hold off on that for now. But I do just really want to emphasize, and I want you to hopefully really start seeing that a slight change in a question can really change the math that you're doing. So do try to think through what you're doing before you actually jump into it. Okay, so again, get through a question, practice actually reviewing these things. I'm going to leave this here for you to go back on with when you rewatch this, when you look at it, and jump right back into these limits that we started with. So limits that we started with, go ahead and think through some that you maybe didn't get through. A couple seconds, think through this for a few more minutes, or seconds, not minutes, a few more seconds, and then I'm going to talk through just a couple of quick things for limits. Okay, great. Hopefully you got through these. Maybe, maybe not. But I'm not actually going to go through these. I will throw a slide up with answers for you in a second, because I know that some of you are just really, really not enjoying not doing this math. And that's wonderful. Wonderful. I'm glad you want to do the math. But I'm going to talk about how to do these kind of really quickly. I want you to remember that the limit of a function at a particular value tells us how the function is behaving as x gets closer and closer and closer to that value. Again, I'm assuming all of these variables are x. When I say x, it could be anything. But that limit is telling us what the function is doing, what that function is actually going to approach as x gets closer and closer and closer to some value. And unless something really weird is going on with our function, that limit should be the actual function value. And I know that is usually our instinct when we see a limit anyway, but our very first instinct should always be to take that value. So for instance, 5 in this first one, throw it into the function, throw it into that expression, evaluate the expression when x equals 5, see what happens. If it gives us a nice, beautiful number, great, there's your limit. For instance, in this first one, we throw in a 5, we substitute in 5 for all of our x's, we get 0 right away. This factor here becomes 0, everything else, then great, 0. When your numerator is 0, the entire fraction is 0. That's also something that generally pops out of our calculus brains sometimes. Be really careful to think through 0 as a numerator, totally fine. 0 over 10, 0. 0 over 7, 0. When 0 is a denominator, that's when we have a problem. So again, our first instinct always should just be to substitute in this value, see what happens. The problem here comes when that leads to something like 0 over 0, like this problem and this problem. When that happens, we want to either factor or multiply by a variation of 1 that includes the conjugate of either the numerator or the denominator. So in this first problem here, or this middle problem here, factor your numerator, factor your denominator. You're going to get 2 factors that cancel, and this becomes nice and easy to work. In this second problem here, what I mean by multiplying by a variation of 1 that includes a conjugate is something that looks like this. Remember that anytime you have an expression, always, you can multiply by 1. Multiplying by 1 doesn't change anything. And that 1 can look like whatever you want it to look like. As long as the numerator and the denominator is the same, great, that's 1. If you multiply by a conjugate here, I'm going to actually go through this one. If you multiply by a conjugate here, we get something that looks like this. I am not going to multiply out the denominator. I am going to multiply out the numerator. And we get this expression first. Now, I see that I have 2 factors that can cancel, kind of. This x minus 16 and 16 minus x, that leads us to a value of -1. 16 minus x over x minus 16, that's a -1. So my function now looks like this. The limit as x approaches 16 of -1 over 4 plus x. And now I'm back to essentially what could have started as a new problem. I'm back to the beginning, take that value of 16, substitute it in, see what happens. That is not right. There we go. -1 over 4 plus the square root of 16, -1 over 8, there's your limit. Also, just very quickly notice that I kept my limit notation the whole way through until I actually substituted in that 16. Once I substitute in the 16, I'm evaluating the limit. The limit notation goes away. Last couple of problems, very quickly. Limit as x approaches infinity. That's one of the ones that generally causes a little bit of panic when we see those, because plugging in infinity, substituting in infinity is not something that is super easy to do. We just get a whole bunch of infinities, plus infinities, minus infinity, over infinity. What in the world is happening there? Remember that a limit at infinity is the pre-calc equivalent of finding a horizontal asymptote. And if you remember how to do that, you have this answer right away. We right away can see that this horizontal asymptote of this rational function would be 2 over 3, if you remember all of those rules. If you don't, that's fine. We can think through what's actually happening here. And the mathematical way to kind of see this, to think through this, is to divide both the numerator and the denominator by the same thing in order to generate a new complex fraction. And this is something that we can talk about again in 2 sessions when we talk about graphs of functions, but very quickly what this would look like is this. I'm going to divide hold on, I'm going to write this out first. But I'm going to divide both the numerator and the denominator by x to the fourth power, because that is that greatest degree monomial in the entire fraction. When you do that, this simplifies really nicely to the limit as x approaches infinity of 2 plus 4 over x squared minus 5 over x to the fourth over 3 minus 1 over x cubed. And now we can go think about substituting in that value of infinity. Substituting in that value of infinity when we have a constant over infinity, when we have a constant over x where x equals infinity, that follows the model of a rational parent function. Think about what's happening to the function 1 over x as x approaches infinity. We get 1 over 10, then 1 over 100, 1 over 1,000, 1 over 1 million. That number is just getting closer and closer and closer and closer to 0. So when this happens here, when we do then substitute in infinity, this term goes to 0, and this term goes to 0, and this term goes to 0. And we end up with just the limit as x approaches infinity of 2 over 3. Well, that's a constant. Great. The limit as x approaches infinity, the limit as x approaches anything of 2 over 3 is 2 over 3. So there's your key for evaluating the limit at infinity if you're not a memorizer, if you're not comfortable remembering all of those horizontal asymptote rules from pre-calc, which again, we will go through in depth when we talk about graphing and how derivatives tie into the functions and all of that in 2 sessions from now. But this is the key that you can do every single time. Divide both numerator and denominator by that same value, in this case, this x to the fourth, and use the value that is the variable to the highest power that you have. Okay, 2 more quick ones. This, hopefully you can see that this is the limit definition of a derivative. This problem, if you substitute in 0, you get 0 over 0 right away. For those of you that are already comfortable with indeterminate forms, which again, I'll go through in a lot more depth in the next session, then this is maybe not that scary. But if it is scary, this is the limit definition of a derivative with an f of x equaling sine of x. And all that this limit is really asking you to do is figure out what the derivative of this function is when x equals pi over 6. So the derivative, cosine of x, the derivative evaluated at pi over 6, cosine of pi over 6, root 3 over 2. Done. If you can recognize that limit definition of a derivative, which again is what we started with today, you can get through these limits beautifully. And then one more, this is just a nice easy one, but I just want you to remember that you do need to know your unit circle values. You need to know your unit circle values. Throwing in pi for your value of x right here, this gives us tangent of 3 pi right away. 3 pi is coterminal to pi, so this is tangent of pi. Tangent, remember, is sine over cosine, so tangent of pi, sine of pi over cosine of pi. Sine of pi is 0, cosine of pi is not. So this entire thing equals 0. Now, we also looked at a couple of oh, there's your answers. This will be up there. I will hold on that for another minute. So if you actually go back and watch the recording of this, you can have time to pause it and look at answers. A couple of very quick things with derivatives, and then we are going to wrap up this first session. This is where we started earlier. And again, I want you to think about how you would find these derivatives. I would need to use a product rule. Within that product rule, I need to use a chain rule twice. I need to use a quotient rule. I need to use a product rule. I need to know my derivative of a natural log function. I need to know my derivative of an exponential function. I need just a nice, pretty basic power rule here. All of that type of information is what I really mean by this. And this is what I want you to really try to think through as you go through these beginning pieces, as you go through these beginning easier problems. Actually think through what you're doing. Actually think through the theory, and that's going to make those harder problems so much easier. Let me leave this screen on for a second. So again, you can go back, watch this, pause, check all of your math, and then wrap up a couple of things. And I'm going to switch back to me for a very quick minute. So that was the first session of just the AP Calculus, the AP AB and BC combinations, units 1 and 2 in the actual AP syllabus. And again, I know that I did not do a lot of complicated things. We didn't do a hard chain rule problem. We didn't do a lot of really any complicated stuff. That all comes later. That comes in all the next sessions, in the hard problems, when we tie everything together. But mastering that concept, that connection between average rate of change and slope of a secant line, and instantaneous rate of change and slope of a tangent line derivative, that being just cemented in your brain is going to help get through so much more in terms of difficulty, in terms of actual speed of working questions, in terms of everything. So do try really hard to master those concepts, to be able to kind of explain all of the things, to do my role of what just happened, to not grab a pencil and do a problem right away, but to tell somebody else what's going on, to tell somebody else what's actually happening with that math, what it means, all of that. So I will hopefully see all of you again next Wednesday. I will answer a couple of these questions. If you did not ask me a question, you are free to just log out of here. If you did answer a question, I'm going to try to run through a couple of these really fast. There's 2 specific ones. Yes, you can use L'Hopital's rule. Good question. When we go through indeterminate forms next session, we'll see that. That's a great use of that rule for the function that just, for the limit, that was the limit definition of a derivative. Yes, you can. You can. Okay, and there was one more question that I just found. Why isn't a curve integral enough over a cusp? Okay, that is a great question, and I'm going to, yes, okay, so if you are still in here for this question about a cusp curve situation, I'm going to answer this in 1 minute, and then I'm going to log off for the next webinar, but I will talk about that in depth when we do the graphical analysis, which is 2 sessions from now. Not next week, but the week after that. So there's a big difference between continuity and differentiability. When we talk about the cusp, the function is continuous at that cusp. The limits are equal to each other. Okay, the limits are equal to each other, but it's not differentiable. Just because a function is continuous does not mean that it's differentiable. All differentiable functions are continuous, but all continuous functions, everywhere that it's continuous, it's not differentiable. So that's a really quick answer. Go ahead and email the classes link at the bottom of the old screen, classes@prepmatters.com, and I will give you a much more in-depth question or much more in-depth answer to that. So I'm going to log off now, and I'm going to see hopefully all of you again next week.